Hello there. In this video we're going to talk about some of the connections between a rational function and its graph. Later on we'll go more in depth where we start with the graph and then try to create the rule for the rational function, or vice versa, where we start with the rule for the rational function and then try to create the graph. But right now we're just going to look at the connections between them. So one of the first things that we would like to do in this kind of problem is, this is not the nicest form, and let's try to simplify that. So I can see that a 2 gets factored out of the top, and then I would be left with x squared plus x minus 12, and you can factor that. So that would give us the numerator, and then the denominator is also factorable. So I'd like to convert these into this kind of factored form, and this kind of factored form actually tells us all kinds of information, like when the numerator is going to be 0. So like if I stick in a negative 4 here, I'm going to have 2 times negative 4 plus 4 is 0, so 2 times 0 plus something. The whole thing's going to be 0 divided by some other stuff, but that's just going to be 0. And at negative 4, we'd see that there is an x-intercept. Then the other time when the numerator is going to become 0 is when x is 3. Stick in a 3 here, 3 minus 3, that's going to be 0. The whole thing's going to wind up being 0. And we can see that on the graph here, that I have those two x-intercepts. Then, so that was when the numerator was 0. What about the denominator equaling 0? Now, later on we're going to get into issues of wholes and such, but kind of one of the things is, like, if I stick in a 1 here, I would be dividing by 0, and that's not allowed, and that doesn't occur in the numerator either. Same thing for the 5. And if we have access to the graph, we can see that both 1 and 5 are what we call vertical asymptotes. There's our vertical asymptotes. We got it at both 1 and 5. And that's actually also going to tell us our domain, because we're undefined there. When we stick in a 1 or a 5, we're dividing by 0. And here we're going down to infinity, here we're going up to infinity. We're undefined there, so that's part of our domain. And we could also talk about range here. Generally, we're not going to do that much in these rational functions, but you can see that this one here is actually hitting everything. So there's no gaps in this line, and it's shooting up to infinity and down to negative infinity. Here, so actually there is an asymptote that this is also getting closer and closer to. So there is a horizontal asymptote. And you can kind of see where this is. Now, horizontal asymptotes, like, sometimes they lie perfectly flat in this axis. Doesn't seem to be happening in this case. Sometimes it winds up not being a horizontal asymptote, but rather a slanted one, an oblique asymptote. This one winds up being horizontal, and we'll also do this more later, but the trick is to look at the largest powers. So they're both x squared, so they're going to even each other out, and then you divide the two coefficients, and you get 1. So our horizontal asymptote is at, not x, what? Horizontal asymptote is at y equals 1. No, not 1. What am I talking about? There's a 2 there. Divide those, and you get y equals 2. And that's what we're seeing up in this graph here. This one has no holes. We'll talk about that more later. And also here we had access to the graph, but you can kind of imagine doing this where if I have the graph and I can see visually where the x-intercepts are and where those vertical and horizontal asymptotes are, trying to create the rule. Or if I just have the rule, then I can look at the numerators to get the x-intercepts, the denominators to, denominators to figure out the domain, and then the potential locations of vertical asymptotes. There's going to be an exception. And then the coefficients and powers to figure out horizontal asymptotes. Here we kind of did it together. We'll break it into more pieces later. All right, thanks for watching Character and Scholarship for Life.